So I found that Monday is a holiday. Yeah, I know. You guys have been working so hard. You've been laboring over this thing. You got a Labor Day holiday. So obviously that means that you have a little more time for that review, because I think that you need to have it ready by before Thursday's class. And also I actually, I'll probably get to start talking about landmark heuristics only like on the Monday after that, because I think today, by the end of today's class, we'll start talking about planning graph. We might talk a little bit more about it next class, and then we'll do landmark heuristics. Okay, so that's where it's going to go. And then, any questions? Okay. Last meeting, we were looking at regression and progression and the potential trade-offs between them from the point of view of search without any heuristic. That is just from the blind search point of view. There is a pretty strong incentive to use regression because people think they do reasoning based on goals. And yet, I pointed out that from a combinatoric search point of view, you can wind up having states, partial states, which are actually inconsistent. Okay, whereas the advantage for progression is states that you generate are always consistent. Okay, so this is some problem. This is a problem that you live with forever, very much, because you can make a progression go arbitrarily. You can make a progression go arbitrarily bad by essentially introducing large number of irrelevant facts into the state. And now, why, the very fact of saying what facts, what should be there in the initial state, should somehow, anything that's in the initial state should somehow be connected to your goal, that's not a reasonable assumption. Because you only have one head, irrespective of whether your goal right now is to come to this class or to, go to grocery store, etc. And all the facts are always there, and you have to figure out which facts are relevant, and you don't do actions just because they can be done. You do it because it's relevant somehow to the current goal at hand. So there is a lot of cognitive reasons as to why you would hate progression and you would love regression, but combinatorially making that work in search is interesting. We keep seeing that trade-off. So one other thing before we move on is actually, so I want to, why do I want that? I don't know. You could actually think of any search as essentially inversion of a way of proving the correctness of an entity. This is a useful way of thinking about where search algorithms come from. Okay, if you know, so before you search for something, you have to ask yourself, if it came and bit you, would you recognize it? Okay, if you don't know, even if the solution came and bit you, you still don't know that it's a solution, then there is no point in searching for it. What are you searching for? You have no idea. Okay, so the way you recognize it is by proving its correctness. Now remember that we haven't gotten into this notion of optimality. Among all the solutions, I want the optimal plan. That is something that you may have in the back of your head. I'm not talking about that right now. I'm just assuming you want to find a correct plan. So the question is, how do you prove that a plan is correct? Okay, in the two search algorithms that we have already pointed out, I gave you two ways of proving the correctness of a plan. In essence, even though I didn't say it that way. One way is, if somebody were to give you a plan, you can progress it. You basically can project it from the initial state, and if the final state that you get satisfies all the goals, then it's a plan. That's one proof. Okay? The other proof was you start from the goals and regress the goal state over the action, over the plan that's been given to you in the backward direction, until you get to, until you exhaust all the actions, and the final state is, you should basically think of them as set of sub-goals. If these were goals, you do this action as the last action, then you would have these as the sub-goals. And then if you do this action as the last action from here, then you would have these as the sub-goals. Now if all the actions are over now, if this were to be the plan, these sub-goals somehow are already vacuously satisfied in the initial state. That's your proof. Okay, if it is, then the plan is correct by regression. Okay, if you prove it this way, then it is satisfied by progression. Both are equal proofs, but now which proof you use, you invert that will give you a search. Okay, if you start with this as the proof, you invert that, you get a search. You start with this as a proof, and you invert that, you get the regression search. Now the interesting question is, are these the only ways of proving the correctness of a plan? And I would argue that in fact there are other ways in which we prove the correctness. In fact, one intuitively very compelling way of proving the correctness of a plan is you look at the plan, you look at what goals you need to satisfy. Okay, let's say these are the goals you need to satisfy. Here is the plan. You sort of try to argue for yourself that okay, in A must be true. Somebody must be causing in A to be true. Okay, the only way things get caused in the strips actions is there is an action which has an effect called in A. That means that it says in A will be equal to true. Okay, and you can actually think of the initial state as a dummy action which just arbitrarily gives a whole bunch of things to be true. Okay, so for this in A to be true, there must be some action including this dummy initial state and these two pink actions. Okay, one of which basically must be giving in A. So that's establishment of the goal. Okay, and then having established it, so if you believe this guy is establishing it, then between him and here, in A doesn't get violated. Right? The way you actually get a goal to be holding is somebody caused it, and after it got caused, it remained true. Okay, the simplest way actually is when it remains true after causation is to just say unclobbered. That means no possibly intervening action has removed that effect. Now I say delete the effect, but really if what you want is var1 to have val7, and if this guy is giving var1 to val7, anybody else gives var1 a different value, they are deleting the original value. Because remember, a variable can only have one value. Okay, so the question then is for this goal to be satisfied, there should be an action somewhere in the plan that gives it, and after that guy, nobody deletes it. Actually, it turns out that interestingly enough, for in a minute I'll show you a pathological example. To capture all the possible examples, you need to actually say that for everybody who deletes it, somebody adds it back. Okay, basically that's because sometimes it becomes hard to pinpoint exactly who is making the condition true. Okay, so in fact the classic case in point is this problem here, where essentially P becomes true here. You can go back and look at it, and I might also mention it in the class in a minute, but P becomes true here. This guy is giving P, this guy is giving P, and so, but we don't quite know who is giving P. And the reason it matters is, if you believe O1 is giving P, then remember these are partially ordered right now. In fact, this is a different kind of ordering. It's partial ordering basically means that this must always be before this, not immediately, but somewhere before this. This must always be before this. But there is no ordering restriction between these two and these two. So they can be interleaved in any which way. So because of that, if O1 is giving P, it's possible that the way you actually execute this plan would be O3, O1, O4, O2. That's not a wrong execution. That's allowed. And if you were to execute that way, then this guy would have deleted P. And you said once it's established, you cannot delete it. So by the first clause, it looks as if P is no longer true, but you realize that P will still be true because, and in fact, one way of catching it, you can either think of it as saying these two guys together are making sure that P will be true in every ordering. Okay. Another way of making it, understanding this is once O1 makes it true, for anybody who deletes it, for anybody who possibly deletes it, there is somebody who necessarily comes after them, necessarily comes before where the goal is needed, and necessarily adds it back. And this guy has nothing better to do than sort of making things right again, and so we call them white knights. Okay, damsels in distress and white knights, and so this is a white knight step, which just sort of comes in, necessarily comes in any time, there is an actual problem, it will necessarily come in after that deleted condition, deleting step, and adds it back. That's another way of thinking about it. So, but coming back here, I can now start thinking of proof of the entire plan to be proof of individual proofs of correctness of every condition. And now the plan would be correct if all the conditions are correct. So you just have a conjunction proof. Now of course, it's not enough to just say in A would be satisfied and in B would be satisfied, because these actions are hanging around, their preconditions are also subcodes, essentially. So in fact, this and this and this and this also need to be shown to be correct. Need to be shown to be established and not violated. Okay, depending on how you look at this, this might be a better way of proving things or worse way of proving things. Okay, tell me why this could be, so tell me both ways. Either way, do you have any idea as to whether this is better way of proving this or worse way of proving this compared to these approaches? You see, for example, this could be a better way, for example. If you have a really large number of actions in the plan, okay, and all you are trying to prove is that a certain condition will hold, this will allow you to do localized proofs. Okay, whereas this one, essentially these are sort of a global proofs. The entire thing has to be progressed and you just look at the final state. Here the entire thing has to be regressed and you just look at the final state. Okay, so if you agree with, if you think in terms of this kind of correctness, so here is another reason why this kind of proof of correctness is useful. If a plan, you started working, you made a plan and you're trying to execute it, you find something is going wrong. You want to fix it. Okay, this proof tells you what part has gone wrong and you can just fix that part. Whereas this proof tells you, well, your progression is not working, or well, your regression is not working. So the failure of the proof in this case sort of localizes what repairs need to be done to the plan. That's another reason why people are interested in this. Okay, so this is basically a causal proof of the plan. And if you now invert this, remember, I got you into this by saying these two were really proofs which were inverted to give progression and regression. And if you like this proof, if you invert this, you'll get a new search algorithm. That would be essentially trying to search for a plan by proving it to be correct according to this proof. Okay, having said that, I should mention to you that normally in a search algorithm, the way you generate candidates and the way you test their correctness doesn't have to be one and the same. So in fact, you can generate candidates using progression refinement, and the termination condition checks whether or not the plan you have is correct using this or using this. There's nothing wrong with it. Normally what happens is that winds up being inefficient, because if you are doing progression both for refinement and for correctness, then you can sort of do finite differencing. You can say up to this part is what, I already have the plan correct up to the, all these goals were true in the previous step. Now I just have to make sure the rest of the goals became true. Okay. Whereas otherwise, every time you're looking at the plan and recomputing its proof of correctness from scratch. Okay. So on one hand, you think of the way the plans are expanded as a refinement operation, and the refinement can happen either through progression or through regression or through the inversion of this I'll talk about, which is called essentially plan space refinement or partial order planning refinement. And then you can test their correctness using any which way you want, but normally a given planner typically uses one refinement and the corresponding proof structure. Okay, so that regression planners use regression as the proof, progression planners use progression as the proof, and so on. Okay, now the question of course is, how do I generate a plan such that by construction, by the end of the search strategy, this plan would be correct according to the plan space proof, the causal proof. And if so, then I'll be done. And so to do that, in essence, this is actually also called the plan space planning, because one of the funny things is in both progression and regression, what you're trying to generate is a plan, right? The solution you're trying to generate is a sequence of actions, a plan. But you are not searching in the sequences of actions. You really are searching in the state of, in the space of completely specified states, or in the space of partially specified states. You're never actually directly manipulating the plan itself. The plan is almost a byproduct of finding path from one node to another node. Okay. So the question then is, the reason this is called plan space planning is because when you try to make something true by this, you directly start thinking about plans. Okay, you start with, the idea would be that, let me show you an example first, and then I'll talk about the actual algorithm. So here's a very simple example. Make sure that you understand this, where I have action A1, which A1 takes M and gives P and not N. Okay, I'm assuming Boolean variables, okay? And similarly, A2, this is A1, A2 takes N and gives Q. Okay, and in the initial state, I have M and N are true, and what I want to make sure by the final state is P and Q. Okay, now what I would do in plan space planning is I'll start with a null plan and see if the null plan already satisfies the problem because of the causal proof. If not, I'll make it incrementally satisfy more and more parts of the causal proof. Okay, that's basically what happens. So I start, what's my null plan? It turns out that in the beginning, the initial state is basically T0. I mean, it's, you think of this as step 0. For reasons that become clear, we'll think in terms of steps, not actions. Basically, the reason is a plan should contain steps, because a particular action instance might occur multiple times in the same plan. And so you need to differentiate the different instances and you call them in terms of different step identifiers. Okay, so this is basically step 0, S0. You think of this as step infinity, because it's the end of the plan. Step S0 is a dummy step which has no preconditions, only effects, M and N, it just gives M and N. And it's already part of the plan when you start. And step S infinity is a dummy step. It basically has either no effects or it has an effect done. That means I'm done with the plan. Okay, and all it requires is all the goals become its preconditions. Okay, and now initially all I have is a plan saying S0 comes before S infinity. And this ordering is the precedence constraint. And it's actually important to understand the difference between a precedence constraint and the kind of orderings that were implicitly coming in regression and progression. In regression and progression, you have contiguity constraints. So if, for example, if A1 is the first action, that means from the beginning of the plan and before A1 starts, nothing can happen. Okay? Whereas a precedence constraint only means that this action should be done after this action. Many things can come in between. Okay, again, this is also cognitively, if you think in terms of, let's say, how you would be, yes sir?
I don't quite follow, because the precedence constraint, at least how you see the written it, is a constraint on states.
No, these are not states anymore. I think of these as dummy steps. So there is an action, I'm sorry, I should keep this here. A1, E, and N, and okay. No, so my plan, my initial plan are two steps, S0 before S infinity. These are not states. S is to stand for steps. Okay? And when you start putting actions, let's say A1 is put in the action, you would say S1, A1. That is step 1, which actually happens to be the instance of action A1. Okay? And now these two actions are such that S0 is necessarily preceding S infinity, which is the null plan. And S0 has only effects, which are what is true in the initial state. S infinity only has preconditions, which are what are required to be true in the final state. Okay? And now the advantage, of course, is that now it does look like a plan. You see if the plan is already correct. So for the plan to be correct, you consider the preconditions of each of the action must be established and unclouded, unviolated. That's all. And if you just keep track of all the preconditions that needs to be established, and make sure that all of them, once established, have not been violated, then you're done. Okay, so in the beginning, this is, I wrote S0, essentially I wrote the I before G, but think of them as S0, S infinity. And then G happens to be having those two goals. And so the goals actually are with respect to a step. That makes sense again, because later on we'll put actions into the middle and they will have goals too. They'll have their precondition as the goals, but those are things that need to be true right before the action, not by the end. Okay, so the terminology you use is, these are called open conditions. A condition which is required at a step, but it doesn't yet have a committed establisher, is an open condition. By the end, you don't want to have any open conditions. Okay, and then the other thing you do is, if you took an open condition and closed it by providing it an establisher, you committed somebody to be an establisher, then in that search branch, you will fight tooth and nail to make sure that that establishment holds. So anybody tries to come in and tries to violate that condition, you will have to either push it out of that range this way, push it out of this range this way, try to reason with it to say, please don't do it. And it turns out it's like there is a way of doing it. So for example, crossing ahead, suppose there is S1 gives P to S2 and S3 is coming in between and threatening, and S3 can potentially come in between. So currently the ordering is like this, let's say, and S3 basically says M implies not P. Okay, so this is the kind of quote-unquote terrorist step who can be reasoned with. Okay, so this guy basically says, I'm really going to blow up P if you give me M. So then I'll just give you not M, so that you won't blow up P. Okay, so all I make sure is, right now I will put not M as a sub-goal to be made true before S3. That's one way of stopping S3 from deleting P. Another way is to take this guy, deport it to this side or deport it to this side. Okay, John Ashcraft, if he was still around, would be very happy because of all my terroristic allusions to simple planning problems. But that's basically what you do when once you make a commitment, you make sure that nobody kills that commitment. Now, where is search here? If I take a condition, I'm trying to decide who can be the establisher. Any action in the library which has that condition can be added to the plan and it becomes an establisher. And for each establisher, I make it in a different branch. Okay? Furthermore, any action that's already currently in the plan, which also happens to have this effect, can be coerced into being the establisher. That's called actually simple establishment, because the difference between bringing somebody from outside, from the library into the plan, and using somebody who's already in the plan is that the guy who comes into the plan, now you have to work on their preconditions. The number of open conditions now is going to increase by the number of preconditions for this step. Whereas the guy who's already around, you're taking care of his needs already. So you're just coercing him to give a little bit more. Okay, so then basically you have simple establishment, some number of branches, step addition, some number of branches. That is just for establishment. And then for every causal commitment, if you do find that there is a threat, possibly the commitment is being violated, there are multiple ways of resolving it. You can, in this particular case, you can resolve it by making not M an open condition, or putting it here, or putting it here. Okay, when none of them can be satisfied without violating the constraints, and one way you can violate the constraints, for example, is suppose the actions, the orderings will introduce a cycle, because you're trying to make this come before something, but there is already another ordering saying it should come after that thing. So it will be a cyclic ordering and the plan is dead. Okay, so in those cases that branch will be killed. Otherwise, you have multiple branches. Just like progression and regression, you have multiple branches for expanding this plan. Okay, so in this particular case, of course, I'll only show one branch. I don't quite know in this example whether there are other branches. We'll see in a minute. But I show you to show that you understood the search. You can show me just one branch that works. And of course, your search algorithm doesn't know which branch works, so it will do all the other branches until it hits on the right one. Okay. So in this case, you start I before G, and then suppose I decided to work on the first on the open condition Q at G. In the beginning, there are two open conditions for this plan as a whole, and no unsafe links. That means unsafe link essentially is a causal commitment you made for which there is a threatening step that you have identified. That would be called an unsafe link. Okay, so currently there are no unsafe links because there are no links yet, no causal commitments, and there is basically open conditions. So you pick one open condition, Q at G, and then there is the initial state doesn't seem to give Q because it only gives M and N. So simple establishment is not possible. The only thing possible is step addition. So you look at all the actions, there is only one action which seems to give Q. So you throw that in. In fact, what I should really be doing is S1 A2. You throw an instance of A2 into the plan, call it step S1. If you again later on throw one more instance, that becomes S9 or something. Okay, so I threw A2 in. Now I want to remember that the reason I put A2 into this plan is to give Q. So I'll just remember a causal commitment saying from A2, from S1 all the way to S infinity, Q must be defended. That's it. Okay. So while we do work to make other things true, Q would have to be defended. And whenever somebody tries to violate Q in that range potentially, you find it. You indicate a threat and you resolve that threat. Okay. So then you work in this particular case. I put a link, and there is no unsafe links yet. So the only other thing that stops this plan from becoming a plan is one more open condition. Okay, in fact, by the way, I forgot, no. Actually, when I put A2 in, remember that A2 has a precondition, which is N. So each precondition now becomes an extra open condition for the plan to work on. So originally, plan had to only make P to be true at the infinite, the final step, P and Q to be true at the final step. Now it also needs to make N to be true at this step. So after this particular plan, you have two open conditions left, and you pick one of them. Okay, suppose I pick P at G. Okay, then what happens? I can basically, by the same argument, there's only one guy who can give P, A1. So now when I put A1 into the plan, I don't necessarily order it fully. I order it just so much that the job is done. Okay. For A1 to be providing P to G, A1 must be before G. Because unless you think causation flows backwards in time, A1 must be before G if A1 has to be providing G. And furthermore, nothing can be before the beginning of the plan, the symbolic beginning of the plan. So the only orderings I put right now is that A1 comes after T0 and it comes before T infinity. In some sense, this is not surprising at all, because any step would have had to come between this and this. But if in fact you're trying to do a condition for some action before G, you would basically make that come before that, because you need to come before the person, the action for whom you're providing a condition. Okay, so now I have two open conditions are gone. One open condition is left, N at A2. Okay, and of course I threw in, when I threw in A1, I added one more open condition, M at A1. So remember, the open condition started with 2, reduced by 1, increased by 1, reduced by 1, increased by 1 again. Okay, so the open conditions make a non-monotonic progress. Until they become 0, you're not done. Until the set of open conditions became empty, you're not done. And when you're trying to take care of one problem, you sub-goal on a huge number of other sub-problems to solve. That's just the way planning works. Okay. So now, this is the first time you actually can. So in my case, I decided to work on the other open condition, which is N at A2. And to do N at A2, who is giving n? Nobody is giving n except the initial state. This problem is simple. There's not too much choice. I made it in such a way that there's not too much choice. Okay? So only one guy is giving it, and so that's a simple establishment. I put, those curved links are essentially, I wrote it graphically, but it's just a causal commitment that you are keeping track of. It's two steps and a condition, such that between those two steps, that condition must be made, kept true. Okay? So I made this. Okay? Now what happens? Now essentially I have only one open condition left as far as I know, m at a1. M at a1 is still left. I haven't yet worked on it. So right now I have one open condition m at a1, but this is also the very first time I have an unsafe link. Do you see that? The reason is a1 can delete n. In the current plan, a1 can come between I and a2. Because they're partially ordered. You see that? Okay. Now, of course, if the plan becomes big enough, you don't see it, but your program is supposed to capture these things. Okay. And so you'll realize that, oh, a1 can potentially come between I and a2, and it is deleting what I'm trying to protect. So you need to take care of a1. Like I said, there are three things you can do when some step threatens. Try to promote, basically make it come out of this range to be before this range. Demote, make it come after the range. Make it come after what range? What is the range we are trying to protect in this case? I'm trying to protect n between this step and this step. So a1 has to either come before this range or after this range, or you should look a1 into the eye and say, don't do it. Unfortunately, a1 is one of these, made up its mind. It's going to do it. As long as a1 is present in the plan, it's going to remove n. It's not a conditional effect. And if you don't have a conditional effect, you can't reason with that action. Right? It's made up its mind already. Okay? So the third option is gone. After two options that are left, promotion and demotion, to make promotion happen, a1 has to come before the beginning of the plan. Makes no sense. Everything is supposed to come after the beginning of the plan, so that cannot happen. So only one idea left, which is come after. That still works because a2 is not the end of the plan. So I decide to work on this unsafe link in this particular case, and then I put in this ordering, a2 to a1. Once I put a2 to a1, now a1 is outside of this range, and done. That unsafe link is done. Now the only thing left in this plan is one extra open condition, m at a1, and that won't cause any extra problems. M is only true by the initial state, and I just put a little causal connection from there, and then look around to make sure that all causal commitments are still holding, and I declare success. Okay. Now this might very well look like the dumbest way to solve this problem. Right? It's like a progression planner would have just tried, the two orders, A1 first, A2, or A2 first, and then it would have worked out which one will work. Okay. What's interesting actually is in a certain way of analyzing the problem, actually, progression planners are pretty bad, approaches for solving problems, because they will, in some sense, try to figure out, reason with all n factorial permutations of the action sequences. Okay, and then to find one, right? Okay, whereas plan space planning is being demand driven, it only introduces orderings as and when needed, and so it can actually do much better. So not surprisingly, when automated planning started, this is the thing that was getting a lot of attention, and nobody would even actually try progression integration ideas because they don't look all that great. Okay, so in fact, the most favorite for, I guess, true old planning research is the partial order planning, then regression, because at least it's goal directed, and then finally, if you have no better idea, progression. And unfortunately, if you now go and look at who's winning all the planning competitions, it's the progression planners. Okay, we'll try to figure out why that is the case and how one can sabotage that, hopefully, so that we can bring back our favorite idea at least my favorite idea back into, because I'm a old planning guy, I like this, okay. Anyway, so that's partial order planning, okay. And if you want to write a little algorithm for this, all you're doing is, a plan is basically a set of steps, a set of orderings between the steps, a set of causal commitments, a set of open links, open conditions, and a set of unsafe links, that means the threatened links. Okay, and you would declare, and the termination condition is extremely simple. The termination condition is you declare success when open condition list is empty and unsafe link list is empty. Then you're done. And in the beginning you start with no unsafe links and an open condition at least, because you should have at least some goal, otherwise the plan is done. At least one or more top level goals, so there are some open conditions and no unsafe links. And in trying to take care of these open conditions, you will introduce actions which will increase the number of open conditions again, and then also as you introduce new steps into the plan, they start threatening the existing causal commitments. And every time you introduce an action into the plan to support an open condition, you remove that condition from the list of open conditions and you put a commitment saying this step is used to give this condition to this other step. And then the unsafe link guy will be looking at these causal commitments to see if any of them, whenever you add a new step into the plan, it looks at all the existing commitments to see if any of them are threatened. And if so, then it puts the list of threats into the unsafe links. Now the planner has to wake up, pick either an open condition or an unsafe link, resolve it. To resolve an open condition, you consider all the simple establishments and all the step additions. To resolve a threat, you consider promotion, demotion, and if you have conditional effects, you confrontation, which is basically you yell at it saying, stop doing that. Okay, and then we will go a little later, so you can actually also have actions which are partially instantiated. It means you might say, there is a step which is saying, I'm going to blow somebody. Okay, basically it's an existential blow. I'm going to blow somebody, and you say, yeah, blow somebody, but not the one I'm protecting. So you just say, so if you have a plan, essentially, let's say if you have a plan where S1 is somehow giving P of A to S2, and then S3 is saying, oh, I'm just going to blow up some random X. Then rather than stop them from blowing up, you just say, please don't blow X equal to A. So X not equal to A. That's the only constraint. You can do your, what you want to do, but just don't make X to be A. Okay, this is what you will need to do if the action is partially instantiated. In fact, we have not talked about partially instantiated actions until now. Okay, and one of the interesting points actually is that when you reason with partially instantiated actions, in essence you're doing a higher level reasoning rather than ground actions. Okay, there isn't much of a partial instantiation you can handle in the case of progression, because progression asks you exactly what action are you trying to do. Regression and partial order planning will allow you not to make full commitments upfront. So in fact, something that you keep talking about, that you keep seeing when you hear about partial order planning, is that it's also been called least commitment planning. It's not the most least commitment planning really, it's more least committed than the other two. Okay, the most commitment planning is progression. Because in every branch it decides which specific action it's going to do, and right after that which specific action it's going to do, right after that which specific action it's going to do. The least committed of the three is partial order planning, because it's just throwing actions in and only putting enough orderings to make sure that the establishments and threat resolutions can happen. The rest is all left open. So what that means is, remember people say don't overcommit. When you actually start doing planning for your own life, you don't necessarily overcommit. You say, I'm going to do this action, I'm going to do this action, and let's say I'm going to wake up, take a shower, and then take a bus, and then come to school and attend Rao's class. This, if you make them contiguity constraint saying shower, and I'll use star to be contiguity constraint. Shower, bus, class. That means you are a horse with blinders on. You don't get to do anything else. You take shower, you get onto the bus, hopefully you'll wear clothes or something, and then you come to the class. No distractions. Okay? Whereas if you don't actually make this plan in your head. You make this plan. Shower before bus, so that you're being nice to the bus people, and then bus before class. And then this allows you to stop by in Starbucks after shower and before bus. And it also allows you to do other things after bus and before class. So you can keep refining your plan with additional actions. Whereas in progression and regression, you made all the commitments. These guys are supposed to come right next to each other. Do you see what I'm saying? So that's another reason why this partial order planning is called least commitment planning, because it's making just the amount of commitments needed to carry through the proof. No more. Okay? So that's it. So you have actions, orderings, links, open condition, unsafe links, and a flaw is either an open condition or an unsafe link. And when the set of the union of flaws is empty, then you get to declare success. And if not, you pick a flaw, resolve it. When you resolve, you get new partial plans. You throw them onto the open list of your favorite search algorithm. And then pick another plan next time around and then work on it. This is partial order plan. Okay? And then I think this is actually what is flaw selection you can pick, and then flaw resolution. And for open condition, there is simple establishment and step addition. And for threats, there is promotion, demotion. And if you have also conditional effects, you have confrontation. And if you also have variables, you can have separation. You require that variable to be separate from another variable, some other value. Okay. So there is a whole bunch of additional comments one can make about partial order planning algorithms. I'll quickly run through them, but you can read them, and if you have any questions, ask me later. Flaws can be resolved in any order. That's a very interesting point. In fact, how many of you remember CSPs? Okay. What do flaws remind you of? What's the analogy for flaws in CSP? What? No, yeah, so is there anything open when the CSP problem, systematic CSP search starts? What are the open conditions analogy in CSP? Unassigned variables. Every variable that's unassigned is an open variable. And as you pick a variable and assign it, it becomes assigned. It's closed now. And when no unassigned variables are left, you are done, if you haven't violated any other constraints. Right? So in some sense, flaws in partial order planning are like variable ordering. Variables in the CSP. And you remember that one of the most important things in CSP is the order in which you assign variables doesn't matter for completeness. It matters for efficiency, but doesn't matter for completeness. Okay? Because eventually all variables have to be assigned, so the order in which you assign them doesn't matter. But you could do much worse with some orders than with other orders. That's why you have most constrained variable would always be assigned first, so that you can fail first. That works here too. In fact, open conditions are exactly like variable assignments, and in fact, so are unsafe links, actually. The only difference, of course, is in CSP, the number of open variables just monotonically reduces. It never increases. Whereas in planning, the number of open conditions is non-monotonically increasing and decreasing and increasing and decreasing, and then at some point of time it becomes zero and then says, stop, I'm not going to mess with this plan anymore. It's just right where I have. I don't have any more open conditions, no unsafe links. I declare success before somebody puts one more action, and I have to start all over again. Right? So there is that connection, and so that connection makes you realize, although that's not a formal proof, actually the order in which you work on the flaws in a partial order planning algorithm has no effect on the completeness of the solution, of the search algorithm. the order does have a pretty big effect on the efficiency of the search algorithm. So one question you should be asking yourself is, what would be equivalent of most constrained variable ordering? And a simple idea would be, for example, you could say any open condition, if you have two open conditions in front of you, one only has one potential establisher, just one step addition. Another has 18 potential establishers, 7 simple establishments and 11 step additions. Which would you work on first? The most constrained one. There you go. So you already have one idea for doing partial order planning. Okay? And in fact, you could go better than that, and you can say, well, this guy has 2 ways. Here is a condition which has 2 establishers. This guy has, what look like 18 establishers. But then these 2 establishers, pretty much any one of them, if you put them in the plan, they will right behind them. This is like, ants of the Amazon jungle coming to your door, and the head ant basically knocks on the door, and you let in one ant, and all the other ants come in, right? And so this one action comes into your plan, all its preconditions can come in. Now, of the 2 top level actions which give this goal, each of them might have 1 million preconditions each. Whereas of the top 18 actions that can give this other goal, maybe they all have some sort of thou shalt not have more than 1 precondition kind of a restriction that they satisfy, and so they don't increase preconditions that much. And so if you really need to be a little better than just counting the number of establishers, if you start being better, that would be heuristics for partial order planning. In fact, we will talk about how planning graph heuristics can be massaged to provide this kind of information for partial order planning. Okay. So a specific order can have a big effect. Open conditions can change non-monotonically. The correct way to order open conditions clause may be to consider how long is the plan needed to achieve each open condition, rather than the number of actions which are providing that open condition. You really want to ask yourself how hard is to actually make it true. This one guy comes in, says, I'll give you open condition, and as soon as you put that into the plan, he has 1 million preconditions, and you are going to spend your lifetime working on those preconditions. Okay? There are many places where the heuristic knowledge can be useful, so the order in which you pick the variable, the open conditions would be helpful. The order in which you pick the resolutions for the open conditions would be helpful. So these 2 are equivalent to variable and value ordering heuristics in CSP. There's pretty much a strong comparison between CSP and partial order planning. Okay, with partial order planning is a more general case. So a special case of partial order planning is CSP, essentially. Okay, order in which, so these 2 you need order in which to resolve flaws, order in which to select partial order plans on the open list. And a third thing is actually one of the interesting things that you will see. I told you about least commitment, right? And in fact, to the extent least commitment is an important thing, you can, in fact, a lot of people, some of you are PhD students, right? Now, what's the worst thing you have to do, commitment-wise? Actually pick an advisor and pick a topic and start working on it. Because if you start doing that, maybe you won't like the advisor, maybe you won't like the topic, and you're stuck. It's like the end of the world. So a smart way to do PhD is not to make a commitment. Keep everything open. Everybody in ASU is potential advisor. Every topic in ASU is a potential topic. This way you will win very big, right? Except you will never know when you are done. You understand what I'm saying? That's exactly true for partial order planning too. So in some sense, a least commitment planner would not make any commitments unless it's for sure. So for example, you might want to know, tell me exactly what will happen if I pick you as the advisor and this topic as the topic. Will I be rich and famous and get to retire by 35? Okay? And unfortunately, I can't tell you that information. So you will wait for that information until way too late, and at some point of time, you still have to make this commitment. Okay? Otherwise, you will, somebody asks you, what are you working on? I don't know. It's like anything, pretty much. Okay? Same thing here too. I'm not saying that you cannot make bad commitments. You can, pick wrong advisors. You can pick wrong topics. That's why we make graduate study ergodic. So you can actually get out of graduates, advisors. You can also get out of topics, and all of you guys will live long enough. Nobody will ever ask you, when did you get done with your PhD? How fast did you get done? Nobody cares, right? Nobody cares. But you would not think about that, and so you keep the least commitment, and that's the kind of thing, since least commitment taken to the extreme can be a bad idea, it can also be a bad idea in planning, in terms of even search efficiency. You can make combinatorial arguments. But neither is overcommitment a good idea. You know, it's like the other opportunity is as soon as you get a letter from the ASU saying you are admitted, you just look at the list of faculty members and press on one of them and say, looks as good as any. Okay? And then send them a mail and say, just give me a topic. I'll start working away. By the time I come here, I'll have read bunch of random papers. Okay? That's overcommitment. Right? And the reality is somewhere in between. Right? And so, in fact, as good as partial ordering planning seems compared to progression, in the sense it's not overcommitting, it can make even less commitment. So for example, one thing that I told you is if there is a thread, it can be either promoted or demoted. Must you make your mind up as to whether you should promote or demote, or must you just throw in a disjunctive constraint, a disjunctive ordering constraint into the mix? And then sometimes if you throw in a disjunctive ordering constraint and later on based on other decisions, this disjunction just disappears. So you'd say it's A or B and you made another commitment saying not A, which means this A or B is now B. Right? So handling disjunction can be a very useful thing in improving partial order planning. In fact, handling disjunction is pretty much the difference between that working on planning in the atomic level versus propositional level versus relational level. Because individual, for a single propositional plan, so you in essence working on disjunctions when you go higher. Okay, so that's the other thing that we mentioned there. Okay, the other thing is partial order planning and regression. What's the connection? They both are goal directed. They start from the goals. The interesting thing is it looks as if the set of open conditions of a partially ordered plan is like the set of open conditions of a partially ordered plan is like the regressed state. It looks like that. The difference is in a regress state, all of them must be holding true at a particular time point. Whereas what the set of open conditions are telling you essentially is for example, P and Q must be holding here, N must be holding here, M must be holding here. So the list of open conditions really don't correspond to a single regression state. Okay. One interesting point, of course, is if you relax the problem. So, of course, if I needed to make, let's say, here's the following thing. So, suppose I needed some, I'm going on a big cross-country trip. Cross-country for me is from here to, let's say, LA. Okay, and I need some candy like halfway through, and then I need some water when I'm in the middle of Mojave Desert. Then I need like a cell phone when I reach LA to call my friend saying I'm here. 3 open conditions. But they're only needed, one is needed at the candy time, one is needed in the desert time, one is needed in the LA time. However, normally most of you, and at least I would do it, and probably most of you would do it unless you are young and arrogant, you would get the candy and the cell phone and water in the car and start. Right? So even though these conditions are required at different points in the plan, you establish them all in the beginning of the plan. And you just need to make sure that there is no candy eating monster in the car who eats up the candy before you started, from between you started and the time when you need to eat. So, as long as you remove all the kids from the car and you're driving yourself, the candy will be there. And typically cell phones don't blow up in the middle of the trip, and typically, water doesn't evaporate. I mean, I know Mojave is hot, but it's not that hot, okay? And so, the reason you could do this, if you did this, it's almost like even though the open conditions are required at different points in the plan, I acted as if they are all required in the beginning of the plan. The reason I could do this is no negative interactions. After the plan starts, the candy won't disappear, and the water won't evaporate, and the cell phone won't blow up. So if I ignore, so if I relax a problem such that none of the negative things can happen, then in fact you can act as if the set of open conditions is like the regression state. Why is this important? Because that then means that when we look at, you guys already looked at planning graph heuristics. To see whether or not a set of conditions can be, how hard is it to satisfy a set of conditions, you can look at the planning graph to see the first index where all those conditions are present without being mutex, and say that's the minimum cost I would need. Okay, I can use that to decide if I have two partially ordered plan, one has open condition set O1, another has open condition set O2, I can see which one looks better by just looking at the cost of those conditions, acting as if before the plan starts I will achieve all the open conditions. Okay, so again, try to combine all the three ideas that we talked about rather than think of them as black boxes which can't be separated, which can't be combined. Okay, so the regression and partially ordered planning are actually very well connected. Both of them are goal directed. It's just that partial ordered planning makes even less commitment. The commitment that regression makes is what? When it brings in an action, it actually decides its position. Partial ordered plans don't decide positions, they only decide precedence. Okay, position means this will be the last action in the plan. That's what regression says. That's a position constraint. Whereas a partially ordered plan says this will be one of the actions that will come between A1 and A7. That can still be multiple different positions. Okay? That's what I would say here. Okay. Any questions on this stuff? Okay. So, handling conditional effects. So, till now, the three different planning algorithms, we just looked at it as if they are mostly about ground actions, ground strips actions. So, preconditions, effects, no conditional effects, no quantified effects, nothing. Okay. So, the question is, suppose I started supporting conditional effects. As I said, you could do some conditional effects either by compiling them out or by directly supporting them. Let's talk about what would be involved if you're trying to support conditional effects. It's interesting because two of the approaches would need to change, one doesn't need to change. Which one doesn't need to change? Progression doesn't need to change. Because by the time you get to progression, by the time you get to a state, you're trying to look at an action which has a conditional effect saying if P1 then Q1, and you are applying it to a state S1. In every state it's completely specified, so either P1 is true or P1 is false. There is no in between, law of excluded middle. It's a completely specified states. So the fact that you have a conditional effect is no better, no worse than you just saying I'll always give Q1. You can easily interpret it at the time when that action is put in front of that state. So progression doesn't get affected by conditional effects at all. Very easy to support them because in some sense progression, you can see this as a good thing or a bad thing. It doesn't get affected because by the time you apply the action, you have to ground it completely. There is no partially instantiated actions, there is no partially specified conditional effects that will be allowed because you have the entire state in front of you. Okay, for regression it's more interesting. Okay, here is an example and think about this. First, don't look at the green, just look at the yellow first. Okay, so suppose A is put in the plan for whatever reason. I have P and Q and I put in A, and A has two open conditions, two conditional effects. J implies not Q and R implies P. Now, how does the regression work? To regress this over this, remember I said first do no harm and then do something useful. To do no harm, I need to make sure that not Q is not actually happening because Q is required in the final state and you can't do not Q. This is when you get to look at A. If in fact it wasn't a conditional effect, A would not even have been introduced into the plan because A is going to do not Q, so you would not regress the state over A. because A has a conditional effect, you will allow it to come into the plan, but you yell at it saying you don't get to give not Q. And the way you say you don't get to give not Q is to, remember, in the previous state, in the state preceding A, remember that you give everything, you are supposed to put all the preconditions of A. In addition to the preconditions, now you put not J. Because by putting not J, it would not give not Q. That's the only way it can be legally present in the plan. You understand what I just said? Okay? Because Q is needed here, and because this guy is threatening to, delete Q, if J is true, then I'll make sure not J is true before A. The only way I can make sure not J is true before A is to make that a subgoal. So apart from M, I'll also add not J to the list. Okay? Okay? And now that way it won't do any harm. Next thing, it needs to do something useful. To do something useful, the only thing that it can do useful is giving P. But even that it won't do it just free. It would give you P if you give it R. So to make it do something useful, you will throw in R into the previous state. Okay, so there are normal preconditions M, and this R is not a real precondition, but it's a precondition that was needed to make A cause B. So these are called causation preconditions. And similarly, you added not J because you needed not J so that it would preserve Q. So these are called preservation preconditions. So when you regress over actions with conditional effects, you throw in secondary preconditions into the previous state. This is ADL representation actually. And so the notion of secondary preconditions is, apart from the required preconditions that you would not live without them, you also, depending on what you're trying to do and what you're trying not to violate, you might have causation and preservation preconditions. Okay, so if you understood that, then I'll mess with you a little bit further and say, suppose action A has two more conditional effects. L implies not Q and U implies P. So it has all these four conditional effects. There's nothing wrong. I mean, an action might give P under two conditions and delete Q under two conditions. Now what do I do? Preservation has to be conjunctive. All ways of killing P must be stopped. Whereas causation is disjunctive. At least one way of causing should be thrown in. Okay? So because of which, I will throw in not L as an additional precondition, additional subgoal. Whereas I don't have to throw in both R and U. The weakest preconditions, in fact, when you do regression, what you compute here, they're called weakest preconditions. The weakest set of conditions that must be true here, so that if you do this, then you will get this. And the weakest precondition is RRU. Because only one of them has to be done. If one of them are true, then you will get P. And so the usefulness clause is satisfied. And both of these guys